So here you have a two-variable function, and you have points P and Q. And the question is, find the directional derivative of this function at point P in the direction from P to Q. So this right here is saying that the unit vector u, by the way, when you do directional derivative, you should always use the unit vector. So the unit vector u should be the unit vector in the direction from P to Q. So let's try to do the PQ, figure out the PQ vector. PQ vector is always final minus initial, right? A vector connecting 2 points is computed by terminal minus initial. So negative 1, 4 minus 2, 0 gives you this vector negative 3, 4. And therefore, our unit vector u would be the normalization of this PQ vector and the size of this vector is computed as square root of negative 3 squared plus 4 squared. Negative becomes positive if you square, so it's 9 plus 16, which is 25. Square root of 25 is 5. So you end up with 1/5 of negative 3 and 4. Now, to actually calculate this directional derivative, we use this famous formula that directional derivative is computed as gradient of the function dotted with u. So that means I need to calculate the gradient. Gradient is defined as it's a vector of all the partial derivatives. In our case, since there's only x and y, it's a two-dimensional vector, fx, fy. So let's compute that. Gradient of f is, you differentiate this considering x as the variable but y as a constant. So these y squared negative 8y, those are all constants. They go away if you differentiate by x. 3x squared differentiates to 6x. And negative 2xy, 2 and y are constant multiples, so you only differentiate x, which gives you 1. So you get negative 2y. On the other hand, if you differentiate this by y, then 3x squared is considered as a constant. If differentiating this by y gives you negative 2x. Differentiating y squared gives you 2y. Differentiating negative 8y gives you negative 8. So our gradient of f at point P, it says at point P, right? So we have to plug in point P into this, would be putting 2 into x and 0 into y. So if you put 2 times 6 is 12, 12 minus 0, so that's just 12. Put 2 there, 2 times negative 2 is negative 4, plus 0 minus 8, so that's negative 12. Okay, so we're almost there. Therefore, the directional derivative of f in the direction u is the gradient dotted with the unit vector, which is 1/5, negative 3, and 4, as we see here, which is 1/5 of, the dot product is component-wise multiplication, and you add, negative 3 times 12 is negative 36, 4 times negative 12 is negative 48, which gives you, let's see, 8 plus 6 is 4, you get negative 84, so you get negative 84 over 5. Okay, so that's the answer to part A. The answer to part A is negative 8 over 5, negative 84 over 5. Let me put a circle there so we know that that's the answer. Now part B, what's the direction of the maximum rate of change of f at point P? Well, this is just asking whether you know the meaning of the gradient. The gradient will be maximized No, the directional derivative will be maximized if you take the unit vector to be in the direction of the gradient. That's because this is really gradient of f norm times the norm of the unit vector times cosine of angle between the two vectors. That's how you calculate the dot product, right? That's the meaning of the dot product. So since this value is always 1, the only thing that controls this value is the cosine of the angle between. But cosine 0 is 1, and that's the maximum value for the cosine. So you're going to get the maximum value of the directional derivative when you're differentiating in the direction of gradient of f. So that means u has to be in the direction of this vector 12, negative 12, and therefore u hat would be the normalization of this vector, and that's 144 plus 144, which is 144 times 2. But 144 square root is the same thing as 12, right? 12 times square root of 2. 12 cancels, and you end up with 1 negative 1 over radical 2, which is 1 over radical 2 and negative 1 over radical 2. And that's the answer for the direction that has the highest directional derivative.